Welcome class. You guys know that we have a test on Friday, so I'm handing out a review over the material. It's about modern physics. So if you have any questions, let me know.
Review? Bro, do you even know what light as a wave is?
No, I don't. What is light as a wave?
Well, I have papers to grade, so Rod will be teaching you instead for today. All right, Rod, do you want to explain that?
Yeah, sure. Okay, so let's talk about light as a wave. Okay, so light as a wave is very interesting. To understand how light as a wave works, you have to recreate Young's double slit experiment. So basically, he had a wall with two slits in it, and he put light through the other slits. And when the light came out, because light acts like a wave, it formed a pattern a little bit like this. And then if you look at the frequency of the light hitting the other wall, it looks a bit like this. And it makes a diffraction pattern this way. The reason this happens is because since we know light is a wave, and waves go through two things called constructive and destructive interference. Constructive interference is when you have a wave that's, as you can see, like this wave, it's on the top, hitting another wave on the top, and it forms a bigger wave because they're both on the top. Whereas destructive interference is when you have a wave that's going on the top with a wave that's going on the bottom equals nothing. And so because all the areas where it's green is where light is constructively interfering with itself. But with the areas which there's nothing, which we'll highlight with red, are the areas where light goes through destructive interference, leading to no light hitting those areas.
Wow, that makes total sense now.
Yeah, I know, I get it a lot
Dude, I
better
get
now.
that.
Thanks, Raj.
Yeah, so...
But I don't really understand
what else
the rest of the review says. Photons and energy?
Yeah, I'm like, what's photons, wavelength, and frequency? Like, what is that?
Okay, so we know that light can be used as energy from like processes like photosynthesis. So the plants absorb the light and then they put out energy. So we know that there has to be some kind of positive relationship between the amount of light, the amount of light and the amount of energy. So Einstein, it was commonly believed in the early 20th century that light and energy were positively correlated exactly like this. When Einstein ran his experiment to kind of like see if that was true or not, he ran it on such small quantities that he realized that that's not actually how it works, but rather the graph goes like this. The reason for that, he reasoned, is because each of the light comes in little packs called quanta, which would be the difference between this and this. And because it comes in little packs quanta, that means you couldn't have an infinitely small amount of light. There has to be a certain, it moves up in certain levels. So that means energy could be quantized, which is extremely important, and that won him the Nobel Prize in 1922. So now we get to the next major thing about light, which is light in the electromagnetic spectrum. So we won't go into all the colors of the electromagnetic spectrum, but we have two main ones. Red. We have red, and then we have violet. Red has the longest wavelength of light. But it has the lowest frequency. Violet, on the other hand, has the shortest wavelength of visible light, but has the highest frequency. So the reason for this relationship is in the formula that the velocity of light equals the wavelength of light multiplied by the frequency of light. So because we know all light must travel at the same speed because it's coming from the same source, we know that if the wavelength increases, then the frequency has to decrease. And likewise, if the frequency increases, the wavelength has to decrease. And this brings us to our next thing, which is that the higher the frequency of the light is, the more energy the light has. So violet, even though it has the shortest wavelength, because it has the highest frequency, has the most amount of energy in the visible light spectrum, whereas red, that has the lowest frequency, has the least amount of energy in the visible light spectrum.
Wow. That totally makes sense now, dude.
Definitely.
I'm gonna pass this now, just because of that. Okay. So
Well, that's only half the review, so
are you serious?
yeah.
What else was there?
Photoelectric effect, kinetic energy of injected electrons.
What? And what's work function? I mean, I work
Yeah.
all the time, but I didn't know there was a function to it. Like what? Okay, whatever.
I have no idea.
What is it like? What is it?
So as you know, during the early 20th century, a lot of the basis of what people thought of light and optics and a lot of scientific basic principles were questioned, like as we saw in Einstein's experiment. Also, many experiments were taken at this time. For example, an experiment was done to see how light would affect a metal substance if light was shined on it in intense enough, in a frequency high enough to cause it to react. So let's say this is our light. And what was noticed was that the light gave out, when the metal plate was hit with light, it gave out small electrons. And this is known as the photoelectric effect. So we did find that, so then basically we were able to determine that the energy of these electrons is determined by Planck's constant, and the person who did this experiment was Planck. And that's H. And so because it's a constant, you'll usually be given it on exam, so you don't really need to remember what it is. Multiplied by frequency. Because you know there had to be a higher correlation with frequency to energy, right? Because when he graphed the frequency of light that was being shined and the energy that was gleaned from the electrons, it looked something like this. So we knew there was a positive correlation between energy and frequency. But when further studies were done, it indicated that there was a certain amount of base energy needed for each metal to give out electrons. So for example, you could have metal A and metal B. Say that they're different metals. If you shine a light of 523 nanometers on each of them, metal B might have a reaction in which it gives out electrons while metal A does not. So it means that because of the nature of the metal, it takes a certain amount of base energy or base frequency to get the metals to start moving. The electrons in the metals. So a new equation was made to calculate the energy given off by the electrons as E equals hf minus, this is known as the work function. The work function is basically what tells us how much energy is gonna be needed to overcome the you could call it the resistivity of the metal to letting these electrons go. And that is the work function.
Wow, thanks, Raj. That helped out a lot.
I know. I finally understand what a work function is. Wow. Okay.
It's not just working out, it's
Yeah.
like there's a whole process
Even
and
though I work
everything.
out all the time. Oh, sorry. Okay. Different. Okay. We gotta learn this.
Alright, still, the last part of the review doesn't make any sense. Atomic energy levels, mass energy equivalents, nuclear reactions,
Yeah.
that like nuclear bombs.
Oh,
What is that stuff?
dude, is that what a nuclear bomb is? I hope not.
Okay, so as we talked about earlier, the early 20th century was a big time of scientific rediscovery. So it was commonly believed before that After Rutherford established what the basic structure of the atom was, which with the nucleus on the inside, which consisted of like a couple protons and neutrons, the protons are in red, with electrons orbiting it at a certain distance away from it, of course.
Teacher, I can't really see that.
Oh, okay. Let me do it in green. So the electrons would orbit around the nucleus. They figured out that through Rutherford's experiments. And basically he reasoned that, kind of like, if you could think of it like a gravitational field, the nucleus pulls in electrons, but the higher energy an electron has, the farther away it can be from the gravity field. Not the gravity field, but the atom's nucleus. So, he basically determined that the distance from the nucleus varies inversely with the electron's energy. So as distance increases, energy level increases, because electrons with more energy can afford to stay farther away. And so as we saw with the photoelectric effect, that when photons hit electrons, they give off energy, as you saw in the kinetic energy equation with the work function. So when a photon comes in, it gives the electrons energy to get farther away from the nucleus. But then this model was questioned because basically what happens when you have an electron that has so little energy, it just ends up hitting the nucleus. And if it hit the nucleus, there'd be some kind of collision, explosion, which we're not really seeing. So that remained unaccounted for. So in the early 20th century, Niels Bohr redeveloped the model for the atom, where instead of the electron going anywhere like it was in the old one, there are certain orbits or energy levels which the electron must go through. And it's only on these orbits that it can orbit the nucleus. Sorry, it's not a perfect circle here, but you get the idea. So basically he got this by checking the energy levels at different distances. So they looked like this. So say you had so this was the distance, right? Say you had 0, 1, 2, 3, for example, and then the amount of energy. So at 0, there couldn't be any electrons because it couldn't be that close to the atom, because because of the structure of the atom, it needed space, and it only works in certain orbits. So that means at 1 meter you'd have a certain amount of energy, and then 2, another amount of energy, 3, another amount. So it's quantized. So you need exactly this much energy or more to get to the next tier of distance, which basically means you can't have enough energy to go halfway. So you can't be at 1.5. You can only be at 1 or 2. So you can only jump from here to here. Any of the excess energy would just be lost. And that's what Bohr's model made. But now, and then it's important next to talk about the mass energy equivalence, which is Einstein's famous equation that the change in the energy of a particle is equal to the change in its mass times c squared. And this is based off the idea that the speed of light does never change, even though it So it's not affected by the Doppler effect. Or I mean, sorry, not the speed, but the frequency of light, and the speed. So it's not affected by anything. The speed of light always stays constant. That's the basis for this equation. So when you have like a mass change, but is not accounted for by. So basically, when an atom is being made, you have, say, you have a proton, a neutron, and one proton. They have a certain amount of mass, but then when they're bound together, their combined mass is lower than their individual masses, which means, according to E equals mc squared, that there is not an equilibrium, but there has to be. So energy is emitted in order to balance the amount of energy, the total energy of the system. This is very important when it comes to nuclear reactions, because when you basically have an atom like the one we had before and you split it, so you're taking it from this to this. But since we know this has more mass than this, to account for the change in mass, energy has to be emitted with this reaction. So when they break, it causes energy to flow. And that's a fission reaction. Whereas in a fusion reaction, if there's enough energy, like we talked about earlier, then it's only with that much energy that you can get it to combine with another one. And that's how fission and fusion reactors work. Fission reactors basically take uranium, which is a very unstable element, and hit it with something that's very stable, which causes the nucleus to break apart, releasing these two, or like not exactly this ratio of neutrons and protons, but you get the idea here. And when they separate it releases energy. And then fusion, on the other hand, when there's already energy present, it takes up that energy in order to make a new atom, or a new nucleus. And that's atomic energy.
Wow, I actually understand physics for the first time. I think I'm gonna do great.
Finally, I feel so confident that I'm gonna ace this test.
Might actually pass one for once.
Finally.
No.
Yeah, no, me too, man. I feel that.